Yeah, as promised, let me now show you a brief code example illustrating the concept of the cross entropy in code using PyTorch. So I have prepared a notebook. I will share it with you. You can find the link as usual on Canvas or here just on GitHub. So let me execute this, just the regular boilerplate. So here I have a function for implementing the one-hot encoding in PyTorch. It looks a little bit arbitrary with this scatter function. I don't really need to go over this because I think there is no other context where I think this scatter function is really that useful. So you don't have to really memorize how this works. If you ever need a one-hot encoding yourself, you can just copy and paste this function. It will do it for you. And also, when we do or train a softmax regression model later, I will show you also a code example for that, and the same for multi-layer perceptrons and so forth. The loss functions in PyTorch, they already do the one-hot encoding for you, so you actually never have to worry about it yourself. But if you ever have to do it yourself, you can just copy and paste this function. So this is just how it works. This is exactly the same example that I showed you on the slides, where we have the class labels 0, 1, 2, and 2. And I have a total number of class labels here. This is the highest class label, or the number of classes, the same thing. So here we have 3 possible class labels, right? 0, 1, and 2. Also note that your class labels should always start with 0. So in this case, what we get back is, for the 4 training examples here, 4 rows, and each has this indicator whether it's this class. 1 is denoting the class, and 0 is it's just a placeholder. So for the first training example, this represents class 0, class 1, class 2, and class 2. Then here's this softmax activation. Oh, sorry, this is actually the net inputs. So this is a matrix of net inputs. I created them just arbitrarily. So each row is again for each training example. We have 4 training examples. So we have 4 rows, and this is how our net inputs might look like. So these are, if I go maybe to the slides, these are the net inputs here. These, and then now we have to apply this softmax here, and then we get these activations. So here's just for reference how the softmax function looks like. And here's a code implementation of the softmax function. So again, there is actually a softmax in PyTorch, so you actually shouldn't use your own implementation, because in the implementation PyTorch is more efficient, faster, it's more optimized, but it's here again to just illustrate how it works. So what we have is in the numerator this exponential term. So when I go here, e to the power of z, and then in the numerator we sum over these exponential terms for all the activations. If we have 3 classes, it will be a sum over 3. So that's what we have here. Now let's do that. So we have our z here. We have 3 classes, 1, 2, 3, and 4 training examples, 1, 2, 3, 4. So these are then the softmax activations that we get back. Notice that the columns should sum to 1. You can just double check that. This max, and then let's do them equals 1. So you can see they all sum to 1, the columns. It's looking good. All right, now just to illustrate how we get the class labels. So if we look at this one again, I mentioned we have an argmax here. Argmax is, you can think of it, maybe I should demonstrate this. It's giving you the position of the highest value. So if I have an example, let's say torch tensor 1, 2, 3, 4, the argmax would be the highest value. So in this way, the argmax should give me 0, 1, 2, 3, the value 3. That's weird here. Okay, what's going on? Oh, okay, sorry. I think I should 4, So I was just not paying attention. All right, so this gives me the value 3 as expected. So if I put a 5 here, this would return 0 now, because now the 0th position has the highest value. If you have a tie, I honestly don't know what happens when we have a tie. What I suspect is it will pick the first value, the lower value. Yep, that's exactly the case. So if we have a tie, it will always pick the lowest value. Okay. So, but yeah, in practice, it will be very unlikely that you have a tie here. I mean, might happen, but it's very, I mean, there could be something like this for the other classes where we have a tie, but usually, yeah, it's rare. All right, and this is, yeah, also only a tie because I put this as a tie. Usually, it's very rare that you have exactly the same values, because that means that the feature vectors look exactly the same, and the weight vectors are that the weight vectors are exactly the same. All right, yeah, let's convert this to class labels. This is just to double check. So these were our true labels from the one encoding. This is just to double check that we that this one indeed converts back to this one. And here these are our predictions. So we used the argmax to get the column with the highest probability. So we get this one, this one, this one, and this one. And you can see there's one wrong prediction if we would compare those, right? 0 and 0, this is correct. 1 and 1 is correct. Predicted class label 0, the true label is 2, this is incorrect. This one is correct. So we make one mistake actually. So it's also, I mean, I did this on purpose to show you how this whole thing works, because if we wouldn't make a mistake, we would get a loss of 0, which would be kind of boring, I think. All right, so here's again the cross entropy. Again, recall that there are two sums. So if I go back here, so we have these two sums here. I kind of entangled them a little bit. So we have, this is a sum over the training examples, and this one is the cross entropy for the one-hot encoding. So this one is the inner one here. So let's compute first the cross entropy for each training example. So what I'm doing here is I'm computing these terms. I actually said that this loss will be 0, but that I don't know why I said that. The loss, even though you match the right class labels, shouldn't be necessarily be 0, except if your activations match exactly your one-hot encoding matrix. Because remember from the logistic regression lecture, we want to maximize the probability for the correct class, but it's only maximized if the probability is 100%, right? So here, even this is correct, even if 0 is the right class, this is not 100% probability. So here we still have a loss, right? Because it's minus log 0.37. Just wanted to clarify, sorry. Where were we? Yeah, so here for the training examples, the losses we get is 0.96, 0.88, 1.05, and 0.83. So this is computing this one, really the inner loop. So these correspond to these computations here. All right, so that is how we would implement this. Now, maybe I can just briefly show you also how that looks like. We are just taking the log of these softmax activations and then multiply it by the target. And remember, the targets are just zeros and ones, right? I didn't define it. That's interesting. Oh, it's in, sorry, it should be, I'm calling it as y_enc, which gets passed to y_target. So let me print it like this. So it's zeros and ones. So I can maybe also print it if you are curious. So this would be one value and the other ones should be zeros. So one value and the other one's zeros in each row. There's only one value that is not 0 in each row. And then we are summing. We are just summing over these. This is the outer sum here. So the first row would be 0.68 so-and-so. Second row would be 0.88, then 1.05. This is actually what we see here, right? So the summing is actually just selecting, it's just selecting the value here. Okay. Yeah, I'm cleaning this up here because when I upload this, so you have the clean version without my weird interjections here. All right, so in PyTorch, there is a function called NLL loss, which takes the log softmax as input. So this function, the negative log likelihood loss, expects the log of the softmax values. I'm just saying that we will use them in practice. We will actually use the cross entropy in practice, but I'm trying to explain how these functions in PyTorch work. So you can see this negative log likelihood loss is the same as our cross entropy here. Like I explained when we go up, I think I had a video on that in logits and cross entropy. So where I mentioned that the negative log likelihood and binary cross entropy are equivalent. In PyTorch, it's actually the negative log likelihood and the multi-category cross entropy are equivalent. I mean, in a way, you can also think of it as a multi-category one, the multinomial logistic regression, then this would be still true. So they are equivalent. But notice it's really important to pay attention to this, is that it takes the log softmax as input. So this might be counterintuitive because there is already a log inside, right? But the PyTorch version does not perform this log here. It expects that you perform it for PyTorch. So PyTorch really thinks you provide this here as input instead of the activations. Just want to clarify this. It's important to note because here we give the softmax as input. Here we give the log softmax as input, right? Because when I just give the softmax as input, I will get wrong results. I will get some, sorry, I just, luckily my glass was empty. All right, sorry. So you notice that now we have negative values here, right? So this is not what we want. So you have to pay attention that this is actually the log. I'm just emphasizing this because it's a common mistake in practice when people implement deep neural networks. They accidentally sometimes provide the wrong inputs and then get weird results, and then the networks are not training. In practice, actually, I recommend using this cross entropy function over the negative log likelihood function. This is numerically more stable. So if you train a deep neural networks, the gradients and everything will be more stable if you use that one. Mathematically, everything would be equivalent if we use negative log likelihood loss or cross entropy in PyTorch. But numerically, like stability-wise on the computer, the cross entropy one is more stable. So, and also for this one, really pay attention to this one. It's taking the logits as input. So it's taking our net inputs as input. So here, again, this is our net input matrix. When we compute the cross entropy, because we use the mathematical formulas, we compute first the softmax, and then from the softmax we compute the cross entropy. In PyTorch, they do all that work for us inside this function. They do it for us. So here we give it the net inputs. And you can see our function takes the softmax, it gets the same results as these other functions, right? So they should be all identical, but in practice this is more stable. I recommend using this one. And notice that I set reduction to none, which means it does not apply the sum or the average, which is this outer one here. So by default, when you use this cross entropy, it will perform the average. You can test it like this. See, it's the same value. If you wanted to, you can also say reduction to, you can set reduction to sum. Sorry, it should be like this. So you can see, you can also do the sum, it's equivalent. But in practice, I recommend using the mean because, like I said, it's more stable in terms of choosing a good learning rate. It's easier to find a good learning rate if you use the mean compared to the sum. All right, so this is like a code example of how all these types of losses in PyTorch work. I recommend you just to play around with that. When we implement the softmax regression in a later video, I will use this function. And also when we use later on multi-layer perceptrons and convolutional networks, we will be using this function. All right, so in the next video, I will go over how we compute the gradients for softmax regression.